In this video, we are going to construct Cantor Set. Step by step, we are going to construct Cantor Set. So Cantor Set has many interesting topological properties. So first, we are taking a closed unit interval C0. So from this, we are going to remove the middle third open interval. So removing the middle third open interval of length 1/3, and let us name that open interval I11. We get C1. It is a disjoint union of two closed intervals, namely C11, C12 is of length 1/3. So and then from the remaining set, the component of C1, we are going to remove the middle third open interval I21, I22 is of length 1/3 square, and we get C2. It is a disjoint union of four closed intervals. So in the next step, in the third step, again we are going to remove the middle third open intervals. So to get the C3, we are going to remove the middle third open intervals, namely, so I31, I32, I33, I34 is of length 1/3 cube. So then we'll get the C3 in the third step. Okay, so it is a disjoint union of 8 closed intervals. So C3 is a closed set. Okay, so yeah, let us see where is C3. C31, C32 is also components 33, 34, 35, 36, 37, 38. Right. So and then C31, it is a closed interval of length 1/3 cube, 0, 1/3 cube, like that. C35, C36, and then we have all the component of C3 up to C3i from 31. Right. So from the construction, what we have C0 is equal to the first step, the closed interval. C1 is 2 disjoint union, C2 is 4 disjoint union, C3 is 8 closed disjoint union, like that. So and then C1 is formed by removing the middle third open interval I11 from the original C0. Okay, so it is a disjoint union of two closed intervals, so it is a closed set. So C1 is a closed set, and then C2 is formed by removing the two open intervals from the components of C1. The open intervals are I21, I22 from C1. It is a disjoint union of four closed intervals, so C2 is also a closed set. So similarly, C3 will be also a closed set. It is formed by removing the middle third open interval from the component of C2. The intervals are I31 up to I34 from C2. It is a disjoint union of 8 closed intervals, so it is also a closed set. Alright, so in general, how we form Cn is formed by removing 2 to the power n minus 1 open interval I and R. R is going from 1 to 2 to the power n minus 1 from the previous step Cn minus 1. So it is a disjoint union of 2 to the power n closed interval Cn. So it is a closed set. Alright, so in general, INR and CNR can be written as follows. INR is equal to KR divided by 3 to the power n, KR plus 1 3 to the power n. R is running from 1 to 2 to the power n minus 1. CNR is closed interval LR 3 to the power n, LR plus 1 3 to the power n. Okay, so the set C, the countable intersection of all these C and it is called a Cantor set. So C is equal to n going from intersection 0 to infinity Cn. It is a countable intersection of closed set, therefore it is a closed set. So Cantor set is a closed set. It is a closed and bounded subset of R, therefore it is a compact subset of R. And from the construction, it is very clear that Cn is a subset of Cn minus 1, and Cn is formed by removing open intervals 2 to the power n minus 1 open intervals from the previous step Cn minus 1, and C is formed by removing all the open interval in all the steps. So length of the interval I and R is 1/3 to the power n minus 1. R is running from 1 to 2 to the power n minus 1. Therefore, the total length of the intervals removed in the nth step is 2 to the power n minus 1 divided by 3 to the power n. So then the total length of the following disjoint union, that is all the interval removed in all the process, is a geometric series 2 to the power n minus 1 divided by 3 to the power n, and the sum is equal to 1. Therefore, the Lebesgue measure of the Cantor set, that is exactly equal to the interval of the 0 1 closed interval minus the length of the interval, sum of the length of the interval in all the steps. Okay, so next we saw that Cantor set is a perfect set. For that we need to show that every point of a Cantor set is a limit point of itself. So before proving Cantor set is a perfect set, we saw that the endpoints of the intervals have never been removed, and therefore the endpoints are in the Cantor set. How we form Cantor set? We form Cantor set by removing the open interval, middle third open interval in each step. So ultimately Cantor set is the resulting set after removing all the intervals in all the steps. Okay, so therefore the endpoints which have never been removed in all the steps will be in the Cantor set. So particularly we are taking two endpoints, 1 by 3 and a 2 by 3. Let us show that in each step these 2 points have never been removed. So in the first step we are removing the middle third open interval, therefore the endpoint 1 by 3 and the 2 by 3 will not be removed. Okay, in the next step again we are removing the middle third open interval. In this case also 1 by 3, 2 by 3 have never been removed. In the second step also we are removing the middle third open interval. In this step also the endpoint 1 by 3, 2 by 3 have never been removed. So in the third step also we are removing the middle third open interval of the remaining set. Okay, the endpoint, all the endpoints have never been removed. Okay, so all the endpoints are in the Cantor set. So let us take an arbitrary point from the Cantor set. Then x belongs to Cn for all n greater than or equal to 0. That means x is in C0 also. X in C0 means x is in either of the component C11 or C12. So if x is in C11, okay, then x should be either in C21 or C22 of the C2. Suppose x is in C21, then we take a point from C22, that is the endpoint of C22. Let us name it x1, and x1 is either on the left or right. Then both x1 and x are in C11, therefore their length is less than the length of the interval, that is 1 upon 3. Okay, next we are assuming that x belongs to C21, therefore x should be either in C31 or C32, the component of C3. Okay, assume that x is in C31, then take another point from C32, that is the endpoint of C32, that is either left or right, and let us name it x2. Okay, both x and x2 are in C21, therefore their distance is less than the length of the interval C21, that is 1 upon 3 to the power 2. In general, x belongs to Cn means x should be either in Cn plus 1 L or x should be either in Cn plus 1 L plus 1. Okay, so we are assuming that x belongs to Cn plus 1 L, then we take an endpoint of Cn plus 1 L plus 1 and let us name it xn. This is how we form the sequence. Okay, and the length of the interval is nth step is 1 upon 3 to the power n, therefore it tends to 0 as n tends to infinity. So we get a sequence which is converging to the point x. So x is a limit point of the Cantor set. So therefore a Cantor set is a perfect set. So that is how we prove the Cantor set is a perfect set. So next we are going to prove that Cantor set is totally disconnected. Means Cantor set doesn't contain any interval. So for that we are going to take two arbitrary points, and the interval joining that 2 points is not in the Cantor set C. Okay, so let us take two arbitrary points. We can find a positive integer n such that 1 upon 3 to the power n is less than distance between the 2 point x and y. It follows that x, y are in the different components cn r plus 1 of cn. So we can find an interval I and L which is not in the Cantor set. So take a point from I and L z, so that z lies between x and y, and since I and L is to be removed from the interval, it is not in the Cantor set. So a point z which is not in the Cantor set will be lying between x and y, therefore the interval x y is not in the Cantor set. So no interval is in the Cantor set, hence Cantor set is totally disconnected subset of closed interval 0 1. So Cantor set is compact, perfect and totally disconnected subset of 0 1 closed interval. So Cantor set can be topologically characterized as compact, perfect and totally disconnected subset of 0 1 closed interval.